When two particles become quantumly entangled, they separate across a void, with their individual states inherently undefined, yet perfectly linked. If you measure one, you instantly know the state of the other. Albert Einstein rejected this spooky action at a distance. In 1935, he argued for local realism, the requirement that particles carry local hidden properties, or predetermined instructions, that dictate how they will react to a measurement. Niels Bohr and the Copenhagen interpretation took the opposite stance. They argued that the properties of the particles literally do not exist until the exact moment a measurement forces them to resolve. For decades, physicists sidelined this as an untestable philosophical dispute. Because both Einstein's local hidden variables and Bohr's quantum mechanics predicted the same measurement results in a laboratory, there was no physical way to prove which description was accurate. That changed in 1964. The physicist John Stuart Bell discovered a mathematical inequality that set a hard limit on the correlations possible if local realism were true. For the first time, experimentalists could test quantum mechanics against Einstein's hidden variables. Over the ensuing decades, researchers ran the tests, and the quantum predictions consistently violated Bell's limits. But the physical testing machines were imperfect. These technical limitations created loopholes, physical vulnerabilities where a determined local realist could argue that hidden variables were still manipulating the data. In 2015, 3 independent teams achieved a milestone. They ran separate experiments that simultaneously closed the 2 major physical loopholes, settling the 80-year dispute with definitive data. The extreme physical engineering required to close these gaps represents a transition from theoretical physics to the high-precision technical control needed for emerging quantum technologies. This schematic details an ideal Bell test. A blue source generates entangled photons, V1 and V2, firing them outward. Polarizers A and B analyze their polarization, routing to +1 or -1 channels. Individual results appear random, but the green coincidences detector reveals strong correlations. Local realism explains these correlations by assuming the central source embedded identical, hidden instructions into both photons before they ever left. To genuinely test Bell's inequality, an experiment has to operate with such absolute physical rigor that no hidden variable could possibly cheat the system by mimicking these quantum correlations. The first major vulnerability is the locality loophole. If polarizer A takes a measurement, it could theoretically leak a signal to polarizer B, coordinating the results to look like entanglement. Even if that hypothetical signal travels at the speed of light, it still requires finite time to cross the physical space between the detectors. The solution is to force the polarizers to randomly select their measurement orientations while the photons are already in flight. To create a large enough flight window, the University of Vienna team separated their polarizers by 30 meters. The team at NIST in Boulder, Colorado, placed theirs over 100 meters apart. At these distances, they utilized ultra-fast switchable polarizers driven by novel random number generators. The equipment locks in the measurement settings fast enough to beat any light-speed signal crossing the gap. By strictly enforcing the limit of the speed of light, the experiments mathematically eliminated the possibility of physical communication between the particles. The second vulnerability is the detection loophole. If your sensors only successfully register a small fraction of the emitted pairs, local hidden variables can skew the remaining data. Historically, physicists relied on the fair sampling assumption, guessing that the few photons they detected were representative of the whole. But unmeasured data leaves a statistical gap where local realist models can hide. To drop that assumption, a system must hit a strict mathematical threshold. The total heralding efficiency must exceed 2/3. For decades, single photon counting technology was too inefficient to reach that limit. The 2015 engineering breakthrough relied on new photodetectors capable of operating at over 90% efficiency. By combining these detectors with high coupling efficiency, both the NIST and Vienna teams achieved a total heralding efficiency of around 75%. Surpassing the 2/3 limit meant local realist models could no longer manipulate missing data to simulate quantum results. While Vienna and NIST focused on flying photons, a research team at Delft University took a different path, using static, trapped quantum bits. The Delft team utilized nitrogen vacancy centers, artificial atoms embedded inside diamond crystals. They separated these stations by 1.3 kilometers. Each atom fires an emitted photon toward a detection station located in the middle. When those two photons mix at the central station, it perfectly entangles the electron spins of the remote atoms back in the distant labs. This event-ready architecture closes the detection loophole. Once the central coincidence signal triggers, the researchers have a 100% detection rate for the entangled spins they have already trapped. Because the atoms are separated by 1.3 kilometers, the physical distance easily handles the locality loophole. The Delft system proved that loopholes could be closed using stationary trapped qubits, demonstrating a method for entangling the types of systems proposed for quantum communication nodes. This chart displays the statistical certainty achieved in 2015. Delft reached a 2 sigma violation of Bell's limit. NIST hit 7 sigma, and Vienna reached 11 sigma, a value so high the probability of a local realist model producing it is essentially zero. These loophole-free tests provide the security foundation for device-independent quantum cryptography. If your hardware violates Bell's inequality without any physical loopholes, the math proves the correlations cannot be dictated by hidden variables. This guarantees the system cannot contain hidden eavesdropping mechanisms. Closing these loopholes transformed quantum entanglement from an experimental curiosity into a mathematically verifiable cryptography resource. Today, there is only one objection left for a strictly determined local realist: the free will loophole. This is the idea that the random polarizer settings and the photon properties were already correlated by an event in their shared deep past, possibly reaching back to the Big Bang. Physicists like John Bell and Elaine Aspect argue that assuming experimenters have the liberty to freely choose their settings is a fundamental requirement of doing science. While metaphysics can always invent a new hidden variable, the 2015 results leave the advocate of local realism with no remaining ground to stand on without rejecting the independence of the experimenters themselves.